Hey, welcome to Ones and Zeros. My name's Ben, and today we are looking at another video in our STM32 Basic series, the first of our videos for 2022. So it has been a bit of a delay since I last put out a video, and finally have the time and stuff to be able to actually get back into it, which is awesome. I'd like to say a huge thank you to all of the new subscribers since I last put out a video last year. And also would like to say a huge thank you to the first of our patrons, which is up there on the screen. So Craig, absolutely awesome to have someone that is helping to support the channel. If you do want to help us out, then I will put a link to our Patreon in the description. However, let's get on to making some stuff happen. So I'm going to be doing a little bit of a simple one today. Do have plenty more videos coming up in this series, but today we're just going to be taking a look at RGB LEDs. So going to be writing a bit of a driver to be able to control either common-anode or common-cathode RGB LEDs, so just the simple ones, not like your NeoPixels and stuff, but just the simple ones so that we can actually get it to display a particular color at a certain brightness level and give us nice easy control over that. So it's kind of adding on to the PWM driver from the PWM video that I've done previously, and using that or leveraging that to be able to control the red, green, and blue components of the LED. So we've got our, let's find where that one is, that's that one there. So we've got our STM32 F411 Nucleo 64 board set up, and we've got the little RGB LED connected there. So that's just a surface mount common cathode RGB LED that we're using there on a little breakout board. Common cathode meaning that it has one input for positive voltage and then a anode, separate anode for each the R, G, and B elements of the LED, and just got the code running at the moment so that it's just pulsing slowly on and off with a reddish sort of color. So it is adding a little bit of blue and green to it, so it's kind of a light red, which is kind of hard to see on the camera, but that's kind of what we're going to be looking at. So if we jump over to our code, we've just got the code as it was after the end of our last STM32 Basics video, where we were taking a look at the SPI or SPI bus, as we can see there. And we've got the PWM driver up from the PWM video. So like I said, we're actually going to be using this to help control the RGB LED, but we're going to write a driver that kind of sits on top of that in order to make that happen. So let's get started on that. So this driver that we're going to write, it will work with both common anode and common cathode LEDs. It's quite flexible that way and allows us to separately control the brightness and the color as well, just to make it a little bit flexible. So let's create us a new header file, which we will call QAD RGB. And of course, the code from this video will be going up onto our GitHub at the end of this video as well. Might help if we name things correctly. Off to a great start for the first video of the year. Awesome, that's got that fixed up. Let's get our header part of this copied over. Pop that in there, change this guy over. Hope all of the people watching had a really good holiday season, Christmas, New Year's, all of that stuff. Hope everyone had a nice, safe one. that is that there. We're also going to need to include in here our PWM driver. So I'll just change that one to PWM, and let's fix this stuff up as well. RGB, and don't even know what the date is today. It's the 14th of January 2022. First file on this code for the new year. Excellent. Alright. Let's grab that. I'm going to copy that and paste that over to our CPP file. Get rid of that one, and we'll change this one to be QAD RGB.hpp. So that's including the header file, and change that one over to CPP like that. So that's our CPP file done and our HPP file sorted. Now, much like we've done a bunch of our other drivers, we're going to use a C++ class for the actual driver. We're also going to create a data structure, an initialization structure to hold the details of how to actually go through and get the driver set up. So we'll get our initialization structure done first. And we will have some videos coming out in this series, hopefully over the coming next couple of weeks, looking at things like controlling servo motors and stepper motors. Also got one that I'm in the process of preparing, which we'll be looking at CAN bus as well, where we'll actually be getting 4 STM32s all connected together via CAN bus. So we can get a really good idea of sort of the ways that that can be leveraged as well. So that's our init structure, and we're going to need to point it, provide it with a pointer to the PWM driver that it's going to be using for controlling the LED, as well as which of those PWM channels it will be using for each of the red, green and blue components of the LED. So I'm just using the QAD PWM channel enums, which are defined in the PWM driver itself. So depending on which time is being used, the PWM can contain up to 4 channels, so we're going to be using one of those and using 3 channels of that. This does require, because we need 3 channels, one of the timers that has 4 PWM channels available. If we jump over to our PWM driver header file, we can see that we've defined that enum in there so that we can tell it which of those channels is connected to each of the red, green and blue. Doesn't matter which ones we use for which, it'll work fine regardless, as long as we've got a timer that's capable of 4 channels. But thanks to the way we wrote that driver, we can actually make sure that that works correctly anyway. I'll explain that a little bit more as we go. These 3 uint8Ts are just going to be used to set the initial color of the LED when it first gets initialized. We'll have another one which is used to set the brightness, and this allows us to have red, green and blue components of up to, so each component can be any number of 256 different values, which gives us about 16.7 million different colors that we can select. Got our last value that we're going to be popping in here, which is to allow us to select between non-inverted or inverted. So non-inverted equals common-anode, and inverted equals common cathode. So because we're using a common cathode LED, we'll need to be using the option to invert it when we go to set up the actual driver to test it. So the driver itself, much like we've done previously, is going to be a C++ class, as I mentioned. And not going to have to use a singleton class for this because we want to potentially be able to have more than one if we've got more than one LED that we want to control independently. So a few bits that we're going to prop in the private section here. So we're going to want a init state enum to be able to track whether or not the driver is actually initialized. Another one to control whether or not the driver is actually active, which will be one of our active state enums. We'll store the pointer to our PWM driver in there as well. Our enums for our red, green and blue channels of the PWM driver. And we also need to store our brightness and our color values and all that sort of stuff as well. So this will be our red value. Our green value and our blue value. Our brightness, which I can't spell correctly, and whether or not we're inverting, depending on if we have common anode or common cathode. We're going to want a constructor for creating this class. And because we're going to need to pass it the initialization structure, we're going to delete our default constructor and create a constructor that allows us to pass a reference to that initialization structure to it. So that will be our init structure, like so. We want a reference to that. And we're just going to call that sinit, and then we'll go through and we'll get it to fill out our member list. So when it gets created, we want it to be set as being not initialized, as being inactive, and then copy across the details from our initialization structure. Our channels, we want our color values, and our brightness and whether we are inverting. Like so. So that is our constructor. And then we're going to need a few other methods as well. So we're going to want some initialization methods to initialize and deinitialize the driver. pop a little comment in there to help break this up. So we're going to want one to initialize it, and we'll get that to return a QA result to let us know whether it succeeded or not. And then we'll have a deinit method so that we can deinitialize it if we need to. We want some control methods to allow us to control what's going on with the LED. Now, it might help if we return the value that we need. So these guys just allow us to retrieve the values that we've set for the red, green, and blue components if we need to, as well as one to allow us to get the brightness and get whether or not we are inverting. And then we'll have some to be able to set those particular details. So to be able to set the red, green, and blue, as well as being able to set our brightness and to be able to set whether or not we are inverting, which will be that one. Now we're also going to want a bit of a private method just as a tool method, which is just going to help us to set the overall color of the LED as needed. So that's those guys. So now we've got all of those declared. Let's go through and create some definitions for them in our C++ file. Copy this guy across as well. And we'll just note that that one's actually private. Again, just to help break everything up a little bit. And what we might actually do is just copy some of these guys across rather than going through and typing everything out by hand. Fix these guys up because they are part of a driver, not part of a system, so they should have a D rather than an S. So I've got our initialization method, which basically goes through and sets the color that we've provided to the driver, and then sets the driver states to being initialized but being inactive. I don't believe we've actually put in any control to control whether or not that is active, so maybe let's get rid of our actual active state because we don't need that one. We'll get rid of that from our constructor as well, and we'll get rid of that from our initialization and deinitialization methods. So we can control whether it's active or not via the actual PWM driver. It might be a feature that we add at a later date, but for the moment it will still do what we need it to do anyway. It means we're not wasting a byte on that particular bit of data. So that's those guys. We're going to pop in our methods to control this stuff here. So our methods to set the red, or to retrieve the red, green and blue components, retrieve the brightness and retrieve whether or not we're inverting. So that's the get methods. Methods to be able to set the red, set the green and set the blue. And we'll notice with these ones, effectively it's copying the value across, so it's storing that value in the driver and then calling set color, which is where it's actually going to be updating the PWM values to draw or to display that particular color on the LED. We're going to add a couple of other methods to allow us to set all three components, so the red, green and blue all at the same time as well. So we'll jump back to our HPP file and we're just going to call these guys set RGB. And we're going to do one that allows us to just hand it 3 UN8T values or 3 bytes, and then we're going to do one that allows us to hand it a combined value, so a 32-bit value that contains the red, green and blue components all in one go, just in case we want to do it that way as well. So let's get the definitions done for those guys and copy those across as well. So this one's just taking those 3 bytes that we're passing to the function or the method and storing those and then calling set color, so similar to what we're doing for set red, set green and set blue. And this one here is doing the same thing but just pulling those values out from the 32-bit value. So as if we're storing those similar to what we would do with a typical 32-bit ARGB value, where we've got the lowest 8 bits store the blue value, the next 8 bits store the green, and the next 8 bits store the red. The upper 8 bits are not being used. That would be where we would typically store, say, an alpha component, which we don't really use for this. We could actually do it so that it could use that upper 8 bits to do the brightness if we wanted to. That would certainly be an option, so we could write a method to be able to do that. But for the moment, we'll stick with what we got. Got another one to be able to set the brightness, and again, it's just calling set color after it's stored that value, and then same with our set invert. It's just storing the value we're passing with it and calling set color. So set color is where basically the stuff gets done to actually update the PWM so that that LED shows the color that we're looking for. So let's get that one copied across as well, and we'll see how that works. So first thing it's going to do is find out what the timer period is from the PWM driver. So the period kind of determines how we're going to go about breaking things up into 255 steps in order to give us the 256 different values. So we're basically dividing that period by 255. Generally, it's going to work best if the timer period is divisible by 255. So such as if it's 255 or 511, things like that. So basically 256, 512, 1024, whatever, minus 1 in order to get to the particular value that we want, if that makes a bit more sense. So dividing the period by 255 to figure out what our increment is for each of the changes in value that we can have. Then calculating a brightness value that we're going to blend with the red, green, and blue values based on, again, the amount of steps that we have to work with. So it's dividing the brightness by 255 and then timesing it by our incremental value. These are all being done with floating point values to make it a little bit easier. So essentially allows us a little bit more easily calculate the overall red, green, and blue values with the brightness blended in. So going through and calculating the floating point versions of our red, green, and blue values. So our brightness value here is essentially going to give us a value in between 0 and 1. And then when it blends it, it multiplies that by the red value. So for example, if our red value was 255, but our brightness was only halfway, which we'd be setting the value to 127, then this bit here would give us a floating point brightness value that's 0.5. So it would then multiply that with the red value. So 255 times 0.5 is going to give us half of that value. So it allows us to do the maths a little bit easier, I guess. Hope that kind of makes sense. Excuse me, losing my voice. Once it's calculated these red, green, and blue values, then it's basically going through and setting the PWM values in the driver for each of those 3 channels. And then determining in here as well whether or not it actually needs to do the inversion. If it does, then it's basically subtracting the red, green, and blue values from our timer period value that we've retrieved up here. So I hope all of that kind of makes sense. So yeah, if not, leave a comment and I'll happily try and answer it as best as I can. Like I said, if you want to check out the code and try and figure out how it works yourself as well, then it will be going up onto GitHub. So that's basically that driver. It's fairly simple. Most of the heavy lifting is being done by the PWM driver itself, which is cool because it allows us to take one driver and leverage it to do a completely different task. So if we jump over to our main.cpp, we'll just tidy up some of the stuff that we were doing for the SPI video. I'm going to get rid of that stuff there and the SPI stuff from here. That's all that stuff there, that can go. And that's basically all of that tidied up. We're going to add our QAD RGB.hpp driver to that one. And then we need to make some class pointers for our PWM and RGB drivers. I've included the RGB, yeah, PWM's there as well. Awesome. QAD PWM and QAD RGB. Just call that those for the moment. And let's get those set up first up. So first things first, we'll go through and actually get the PWM driver set up, and then we can set up the RGB driver and pass a copy of the PWM driver to it. So filling out the PWM initialization structure here, and then creating the class for that. So I'm going to be using timer 1 for this one, which has 4 channels. So it allows us to have the 3 channels that we're going to need for the red, green, and blue. Setting its prescaler to 1000 and then setting its period 255 because that the number of variations that we can have for each of the red, green, and blue colors. So just make sure that everything works nice and smooth. And having our pre-scaler set to sort of a lowish value like 1000 also enables the PWM to work quite quickly. So we're not going to see the flickering or anything like that of the actual PWM. And it also means the timer is going to be updating that nice and quickly as well. So we get nice smooth gradients and things like that as colors are changing or as the brightness is changing. So going through and telling it which pins we're using for each of the 3 channels that we're going to be using. So for each of these channels, telling it that the particular channel is going to be active, which GPIO port we're using, so using GPIO A for all 3 of them, which pins we're using, so using pin 8, 9, and 10 for our R, G, and B respectively, and then telling it what alternate function it needs to use to connect it to the timer that we're going to be using, so AF1 timer 1 in this case, and then telling it the final channel, so channel 4 of the timer is just being set to inactive because we're not using it. Going through and creating our PWM driver, and then initializing that, checking to see whether or not that has initialized correctly. If not, then sending a message out to the serial just to say it's failed, turning on our red user LED and jumping into an infinite loop so that it doesn't proceed if it does actually fail. Assuming that it has initialized correctly, then we're going through and telling the PWM driver to actually start, and then printing a message via serial just to say that we've initialized and started that driver successfully. So that's the PWM part, and then set up the RGB driver. It's fairly similar, so filling out an initialization structure for it and then creating the driver class. So same stuff here, we're passing it the pointer to our PWM driver so it's able to access that, telling it which channels we're using for the red, green, and blue, in this case channel 1, 2, and 3, what our initial values are going to be. Excuse me. It's not COVID, just choking on air at the moment. So this is going to give us a value that is mostly red, so 7F for the red component and then 7 for the green and blue. These values can be set to whatever we'd like there, and we could use non-hexadecimal values, so we could, in this case, that'd basically be 127 and then 7 and 7 if we wanted to. Same thing. It's I find it a little bit easier to do it this way because it allows me to write that whole byte in one go that's controlling that, and then setting our brightness level. So this is giving us a brightness level of 195, so about 75% brightness. That is our initial setting, so mostly red, 75% brightness, and because we're using common-cathode rather than common-anode, we're setting our invert value to true. So going through and creating that driver class, initializing it. Again, if the initialization fails, we just print a message out via serial, turn on our red user LED to let us know at a glance that there's an issue, and jumping into an infinite loop. However, if it succeeds, then we'll just print out a message saying that it has actually initialized correctly. Now, we will test it at the moment, which is just going to give us a solid color. And then we'll go through and actually get it to vary it like we saw at the start of the video, where it was kind of pulsing the red on and off slowly, so it almost looks like the LED's breathing, which is kind of a cool effect. So let's save that. We'll build this. We'll make sure it actually compiles correctly, which is always fun, because we have some errors. Where are errors? Okay. As in the code I wrote preparing for this video, for some reason this was returning uint 16s instead of uint 8s. So that's those guys fixed up, and down here we have okay, because we need to modify the PWM driver to have that get period value, get period method that we are looking for. So let's add that one to it. It's not one that we put in there when we first created that driver during the PWM video. And that will be this one here. No, that's not the one I want. We want this one. That's it. And then we'll copy across the definition for that one as well. Which will be going in there. Copy that over and paste that in. So that's basically just returning the MU period value that's being stored in the driver already. So a nice simple way to make that work. And then that should hopefully sort out the errors that we had. Wonderful. So if we pop that onto our Nucleo board, we should get, once the code finishes uploading, there we go, we've got our LED on and it's red. And we can go through and just to make sure it's definitely working, let's go through and might make it so that it's mostly green and just make sure that that's our color channels are actually set up correctly. So just pop that onto the board as well, and we should see our LED go green in a moment. Like so. So that works well. So nice simple approach, fairly simple driver. Just allows a little bit of an easier approach for hooking up a typical RGB LED if you want to use one in one of your projects. But let's make use of the driver and let's animate it slightly. So we'll pop back over to this one and just up near the top of our main CPP, I'm going to chuck in a constant here to control our how quickly we want this to be updating. And we might get it to update it every 10 milliseconds. So just set our threshold value for that. I want a tick threshold, not a thick threshold. That might help. Good to see my typing's as good on stream as it was last year. That hasn't improved at all. Also not used to doing the videos and losing my voice just from all the talking. Alright, so we're also going to need to go down to our processing loop here, and we're going to want to create a LED ticks value so that we can time the update of that. And we're also going to want to track a couple of bits of data for that. So firstly, our current brightness level, because we'll just get the brightness to increase and decrease as it updates. And which direction we're going, so whether it's increasing or decreasing in brightness. And then let's pop something in our processing loop to make that do its thing. So first thing we're going to want to do is update our LED ticks value with however many ticks have passed since the previous loop. And then if that has exceeded our threshold value, then we're going to get it to update our LED. If it has exceeded the threshold value, we're also going to need to reset our LED ticks value. And to do that, we're just going to subtract our threshold from our LED ticks value there. And then if direction is true, then we're going to go through and increase the brightness. If it's false, then we'll decrease it. So if U brightness equals 255, so if we've reached maximum brightness, then we will change direction and start decreasing the brightness. Otherwise, we will add 1 to our brightness value. And then for our part where we're decreasing it, we'll first check to see if brightness has reached 0. We'll make sure that's a comparison, not an assignment. So if it has reached 0, then we want to change direction. Otherwise, we'll decrement our brightness value. And then once it's updated all of that stuff, then we'll tell the RGB driver to update our brightness value, like so. So fairly simple. That's all compiled nicely. No, I don't want to update this right now. Thanks, still in the video. Let's pop that onto our Nucleo board. And we should get a pulsing green LED, like so. Okay, so we have a bug. So if we have a look at the code, we've told it to change the direction to false if we've reached maximum brightness, which works. However, I've given it the wrong direction for if we reach the minimum brightness, which is why it reached the minimum brightness and stayed there. So we'll fix that up and we'll pop that back onto our Nucleo board, and then that should work properly. And there we go. So we now have our pulsing LED. And we could do it so that we're updating, you know, a particular color value or all of the color values. We could go through and do something a bit more complex where we're actually getting it to go through, you know, a rainbow of colors if we would like to. All of that stuff's fairly easily doable using that driver. And the fact that it allows us to control the brightness separately to the color does give us a little bit more option as far as how we want to do things there as well. So it's a sort of driver that could be fairly easily added to if you wanted to as well. So you could go through and add things to be able to do animations and stuff like that. So you could have like a process method in the driver that gets called at a regular interval that updates things in a particular way. All of that sort of stuff, which is something we might actually look at in a future video. If you're interested in that, feel free to leave a comment and let us know. If you enjoyed this one, I'd love it if you subscribed if you haven't already and liked the video. Again, thank you to all of the new subscribers that we have since I did the last video last year. It's really great to see that people are enjoying the videos, and to all of you who've left comments and likes and stuff like that, thank you a lot, because it really does mean a lot. I really enjoy doing this stuff. It's great that other people are enjoying watching the videos, so that's really cool. And thank you also to Craig, who is our first patron for ones and zeros as well. Again, super awesome. Next video on this series is probably going to be a servo video where we look at controlling servo motors, and again, that's something that's going to be also leveraging the PWM driver. It's similar to this in the fact that we will be building the servo motor driver on top of this PWM driver like we have with the RGB LED one. It was through getting some of the prep work done for the servo driver that kind of inspired this a little bit, especially because I needed some additional hardware to show up in order to complete preparation for that video. So that's where this one kind of came from. So I hope you've enjoyed it anyway, and hope you have a wonderful night or day, evening, whatever it is where you are, and thanks for watching.